Riemannian exponential map on the group of Voigt's diffeomorphisms.
Hey, thanks. So despite the title, the talk will be about hydrodynamics, more precisely about the geometric approach to hydrodynamics initiated by, in 1966 by Arnold. And the ideas of these geometric ideas have already, you could see them already in Sasha's talk 2 weeks ago, I guess. You talked about Arnold's stability criterion. Well, so of course, hydrodynamics, so you will see probably some of these ideas again, maybe in slightly different form. But of course, the hydrodynamics, at least the modern formulation, goes way back to Euler. You know, I'll probably begin with the Eulerian description, which is the high-tech description. But my main concern will be with the so-called Lagrangian description of hydrodynamics. So let me first set the stage, begin with just saying a few words about the two approaches. So in order to describe motions of an ideal, and this means incompressible and viscid fluid in a fixed domain, which I'll take for simplicity to be an n-dimensional Riemannian, compact Riemannian manifold with volume form, Riemannian volume form mu. Well, the two dimensions that are of greatest interest in hydrodynamics are, of course, 2 and 3. So the so-called Eulerian approach has as a starting point the following description of the motion. So we fix a point in this domain, and then we look at the velocities and record the velocities of all the fluid particles that pass through this point at time t. Then I'll vary. If we vary x, we obtain the velocity field. So this is a velocity field. And we require that this field satisfy, it's a vector field on this manifold, that it satisfy the Euler equations of incompressible flows. So here nabla is the covariant derivative. The manifold is Riemannian, so this is well defined. This we set equal to minus gradient of p. P is an unknown function, but we can solve it once we know u, because we add one more, and that's the incompressibility condition here, which in terms of the vector field means that the vector field has to be divergence free. Now, if we add to this an initial condition, we obtain the Cauchy problem, which has a long and distinguished history. So it really, let me say a few words about this. The work on local well posedness for this system of equations in 2 and 3 dimensions goes back, in modern times, goes back to 1920s and 30s to people, well, by local well posedness, I mean constructing a unique solution which depends, in the sense of Adamar, at least continuously on the initial data. So the people who worked on that were Günther, I think, in Moscow, and Lichtenstein in Leipzig. Lichtenstein, incidentally, is the author of a book, one of the first volumes in the Springer series of the Grundlehren series, which is probably still worth reading. I looked for it in the library, I couldn't find it. So I hope it's there somewhere. Okay, so they worked on the local well posedness in any dimension. And this was, as I said, 1920s. Now, Lichtenstein had contacts with mathematicians in Poland, and he convinced, I believe, Wolibner, who worked in Warsaw at the time, he got him interested in this problem, who proved the first global well posedness result, which means he proved existence and uniqueness and continuous dependence globally in time, for all time in 2 dimensions. So this is in 2D, and this result goes back to 1933. So these were early spectacular successes. They were followed by by many other great results. So, for example, Udovich made contributions in, I think, 1963. He wrote a paper on weak solutions. Kato, who worked on and off on this problem. Probably his first paper goes back to 67, and many others. Eben and Marsden, Bardosh, Konstantin, Maida, and so on. So there was a lot of work, and this work still continues. Of course, in 3 dimensions, global well-posedness is a major open problem. But even for the local well-posedness, there is on the local problem, there is still a lot of work that's being done. Yeah, perhaps let me just mention here that what's known currently, I mean, at least as far as I can tell, is that the sharpest result I'm aware of is uses more exotic spaces and shows local well-posedness for Euler in 3D in the space Biesov space. So that's a more exotic space, B1 infinity 1. Rather than describing it, let me just say that that this space is contains C1 plus alpha. Alpha here is between 0 and 1. Eulerian spaces, in which the original results were the question was originally studied, and itself is contained in C1, which is in fact an interesting case because this space is considered to be perhaps a borderline. As far as I know, there are no results in C1 yet. What is known, however, is that if we decrease the regularity a little bit, so once again, alpha is between 0 and 1, and we say consider some weak formulation for the Euler equations in the space C alpha, and we take some initial datum from the C alpha space, then it is known, and this is a result that was recently, there was a paper of Bardosh and Titi, this is I think 2010, who showed that if we start with, who construct a solution such that the initial data is in C alpha, alpha between 0 and 1, but the corresponding solution is not in C beta for any beta strictly larger than alpha squared. So in fact, in particular, the solution will not remain in the space C alpha. So this is an ill-posedness, local ill-posedness result. Now, this can be, I think, improved, and already some constructions that are improving this. Now, the well-posedness result, so this is local well-posedness, in B1 infinity 1 is due to Pak and Park. And again, this is 2005, I think. So there is a lot of work here on this side, but that's not my main concern today, because there is this other description of the motion of fluids, incompressible fluids, which is more primitive, more basic. This is high tech, the PDE formulation. So here is the more basic formulation. It's called Lagrangian. Even though I think it's also due to Euler. Yes.
Are any of the results you just stated actually proved on a Riemannian manifold in the same?
No, I think these, well, okay, so the results that people, that I can think of off the top of my head that where people study the well-posedness of this system on a manifold, are, for example, due to Eben and Marsden, and I will mention this. So I'll come back to that. And they're in L2 Sobolev spaces, where S here is required to be greater than n over 2 plus 1. This will play a role, so I'll come back to that. In most cases, we're actually interested in even the basic results. The simplest space, take 2 torus, 3 torus. Periodic space periodic situation, or Rn, R3, R2. Okay, so the Lagrangian setup is the following. So rather than fixing a point in the domain, we fix a particle. We sit on it and follow its trajectory. So it describes a certain trajectory here in the manifold. Remember, the manifold M is fixed. And I'll call, say, this point at some time, later time, eta of t and x. And this will be the position. So here we're not looking at velocities, but at positions. So eta of t and x is the position at time t of that particle, of that fluid particle, which at time 0 was at x. So we get a trajectory here. If we look at the totality of these trajectories, we get a description. We get the fluid flow. And we don't want these, because we don't want the particles to fuse or to split, we want these to be bijections. And we also want them to preserve the volume. Preserve volume for mu, the Riemannian volume here. So we get as a configuration space of this whole system, here we get a group of diffeomorphisms, which are volume preserving. And this is the starting point, really, for Arnold, who, in his paper, which I mentioned, 1966, reformulated the equations of motion for the Euler equations of motion for an incompressible fluid as equations for geodesics on this configuration space of a certain metric, which I will describe. So the problem is, it turns out that there is a very nice, very beautiful geometry or way to geometrize the problem. And I'll try to describe very briefly Arnold's main observation, and then the following subsequent work of Eben and Marsden, and then focus on my main goal, which is in the title of the talk, the analysis of a certain exponential map on this group of diffeomorphisms whose singularities I will try to describe. Okay, so before moving on, in order to, so as I said, Arnold's approach was to think of the space of volume-preserving diffeomorphisms as the configuration space for the flow and the fluid flow, and to realize the motions, fluid motions, as geodesics of a certain metric. Now, in order to solve for these geodesics, we have to topologize it, topologize the space, and Arnold did not work with, did not really worry much about topologies. In a lot of his approach was just to think in kind of a priori way, a formal way. But I will need topology. I'll pick, therefore, Sobolev topologies. And therefore, let me say a few words about groups of Sobolev diffeomorphisms. Now, these are well-known objects. They were studied already in the 60s. And so I will be mainly interested in just two aspects. I will be interested in these groups as infinite dimensional manifolds, and I'll just briefly describe here what I mean. And then as Lie groups. Well, they're not Lie groups, and I'll also try to describe the problems, the reasons why they're not Lie groups. But nevertheless, almost good enough for at least for my purposes. So first, I will denote by diff with the superscript s. So this will be the Sobolev index of M, or Mn. I want to think of this set as an intersection of C1 diffeomorphisms of M with the space of HS maps from M to M. Okay, so C1 diffeomorphisms, well, this is well known, are an open subset of the space of all C1 maps from M to M, while this space was as I said, studied in the 60s, and perhaps the names that are associated, I don't want to go into detail in describing how one introduces the structure of a smooth manifold in this space. Let me just say that it can be shown to be a C infinity Hilbert manifold modeled on the space of Sobolev maps from M to Rn. M, remember, is n-dimensional, provided that S is greater than n over 2. Well, the main tool here is the Sobolev lemma. So even if I had, say, continuous maps from M to M, I could make this into a smooth manifold. The construction is due to Eels. This, I think, goes back to some paper in the proceedings somewhere in Mexico in 1958. But he has another nice survey article in the Bulletin of the AMS from 66, I think, or 65. I forget now. 65 or 6. I'm not quite sure where he describes this in detail. So there were other, he doesn't really work with HS spaces, so there were other people, Smale, I think, Abraham, Palais. Palais has a book on that, the nonlinear functional analysis, I think it's called, where you can also find the construction. So if S is greater than n over 2, this is a smooth Hilbert manifold, and then if we again use, well, require a little bit more of S, namely that S be not just greater than n over 2, but n over 2 plus 1, then using Sobolev, again, lemma, we can consider a continuous inclusion of this space in the space of C1 maps. And putting these two facts together, we obtain we conclude that diff S will be an open subset of the space HS, and therefore will acquire a smooth Hilbert manifold structure as an open set in a Hilbert manifold. So this is an open subset of HS, hence a smooth manifold, Hilbert manifold. Now the tangent space of this object, say at the identity diffeomorphism, perhaps I can squeeze it in here. So E will be a map, E of X is X, so that's the identity diffeomorphism. So the tangent space to diff S of M at E is just the space of Sobolev sections of the tangent bundle Tm. And if I were to take, say, eta, a diffeomorphism of M, then the tangent space at eta would simply be HS sections of the pullback bundle by eta. So this is the pullback bundle. Okay, so so this is one object, but the object that I'm more interested in here is a submanifold, and I will denote it diff super S sub mu of M. Now this I'll define as the set of all these diffeomorphisms of Sobolev class S that preserve the volume form. So the pullback of mu is mu. And this can be shown to be a smooth Hilbert submanifold. Submanifold of diff S of M, and this is really due to Eben, I think, in his thesis, possibly 1968, where he studied the slice theorem, I think, for the action of the diffeomorphism group on the space of Riemannian metrics. So he was interested in a different problem, but nevertheless in the same object. Essentially, this follows from an implicit function theorem in Banach category. The tangent space at the identity here will consists of all those vector fields, call them little v. So these are all HS sections of the tangent bundle whose divergence is 0. So this is the space of volume-preserving diffeomorphisms, or as I don't know if this will catch on. I'll call them volumorphisms. Well, we have symplectomorphisms. We can have volumorphisms. We'll see. Okay. Now, this is all I have to say about these sets as manifolds. Now, what about the group structure? Well, first of all, so if S is greater than n over 2 plus 1, it turns out that both diff S and diff S mu are topological groups. Topological groups under composition, of course. Now, in order to show this, one needs some Sobolev facts from Sobolev theory about compositions of diffeomorphisms, HS diffeomorphisms with themselves and with HS functions. A lot of this was developed, as I said, in the 60s and can be found, for example, in Palais, even though at least in the case when S is sufficiently big, which is, for our purposes sufficient. If S is so big, then both these spaces are topological groups, but they're not Lie groups because, well, if we look at the map, say xi eta, so this is going from diff S, say, cross diff S, into their composition. So this is now I want this to be in diff S. And this map is continuous. It's a topological group. So it's continuous in xi and eta. But when I look at these, but it's not differentiable. I mean, it depends how I look at this map. So if I look at this map as, say, right translation by eta of xi, then the right translation is smooth in Sobolev topologies. But if I look at this map as a left translation of eta by xi, like this, then the left translations are continuous, but not even Lipschitz continuous. So in this case, what we get is if you, for example, want to compute, so let me just write this as R eta star, for example, xi. If I compute the derivative here, and apply this to some vector W, where W is a vector which is tangent at the point xi to diff S, right? So it's an element. I mean, it's an HS section of that corresponding pullback bundle. Then this derivative, I mean, all we need to do is take a curve through xi and then differentiate this with respect to the parameter of the curve. And you will immediately see that what you get is another right composition on the right. And we can continue doing this. So it's in this sense that we have a smooth map. We can just continue differentiating. But in the case of the left translation, so the corresponding derivative here would involve, well, derivative of xi composed with eta. And then this would have to be applied or multiplied by W. So if this is HS, eta is HS, well, this will be HS minus 1, so there is a derivative loss. This is just one way of seeing why these HS finite irregularity spaces are not Lie groups. So because of this derivative loss, we conclude that there are groups under composition, but not Lie groups, but not Banach Lie groups. However, with respect to right translations, things are fine. So we'll use right translations. So next, let me say something about, Oh, also another thing, the compositions are fine, but the inversion map, I of eta sending eta to eta inverse is also continuous, but not differentiable, not Lipschitz, but not Lipschitz. And it's not difficult to actually do this calculation and see what happens. All right, so now let me describe Arnold's observation from 66. So what he did was to define a Riemannian structure on the group of diffeomorphisms. Well, I'll do it the following way. So let's take V and W, two divergence-free vector fields on M, and I'll define an inner product at the identity, in the tangent space on the Lie algebra, as simply the L2 product. So this is a global product. I'll take the inner product of V of x and W of x in each tangent space on M, and then integrate it with respect to the Riemannian volume form. Essentially what I get is an L2 inner product, which really is essentially the kinetic energy, the fluids, the kinetic energy of the fluid. This is how Arnold was thinking. What's that? Yeah, that's right. So, of course. So when I say, that's why I say essentially. So if we take, in fact, not just V, and V has to be the velocity, of the fluid's velocity in Eulerian coordinates, then we get precisely the L2 energy. So we define this, so he defined this, he started with this inner product, and then used right translations. Well, the smooth maps here will work in our case, R sub eta, to define a right invariant metric on the whole group diff S mu. Now, this is a kind of quick way. There is perhaps a nicer explanation of this, but this will again suffice for us now. Okay, so he did that and then made the following observation. So this is in his paper, the second part of his paper. Namely, he noticed that a curve t goes into eta of t in this group of volumorphisms is a geodesic. It's a geodesic of the L2 metric, of the right invariant L2 metric, say starting at the initial point, which is the identity, with the velocity, initial velocity, let me call this u0, if and only if the curve t goes into u of t, which is defined as follows. This is the right translation of the tangent vector eta dot. So this is a curve in here. Eta dot means the time derivative, the derivative with respect to the curve parameter. That gives me a tangent vector to the curve. I compose it, which means I use right translation by eta inverse. And I obtain an element in the Lie algebra of the group. So this eta is a fluid flow. I mean, sorry, no, not yet. It's a geodesic of the L2 metric. If this right translation is a vector field on M, which satisfies, that solves this Cauchy problem. Okay, how to see this Well, one way to see this is to simply use, that's not what Arnold did, but perhaps the simplest way is to follow the Riemannian analogy with finite dimensions and use first Riemannian principles. I can write down the energy functional of that metric. So the energy functional here, let's call it E of eta, is just 1/2 integral, say, from 0 to 1. I take the tangent to the curve. This is the L2 inner product at the point eta of t, square it, and take dt. I can compute the first variation formula, just as in finite dimensional Riemannian geometry. So if we compute this, so compute the first variational formula as in finite dimensions of the L2 energy of this metric, and write down the Euler-Lagrange equations. So use, localize, use some Dubois-Reymond or something like this. Write down the equations and then make a change of variables. This is the change of the dependent variable that one makes. And what pops out is precisely the Euler equation. Perhaps a picture will, which I like always drawing, kind of to give you some intuition of how to put these things together. So it may help. So the following picture, let me make the following picture. So let this be the Lie algebra, the tangent space at the identity, TE diff mu s. Here is the 0. This is upstairs. Now let me go downstairs. Downstairs I have the big space of diffeomorphisms, volumorphisms, Sobolev volumorphisms. This is where the identity diffeomorphism is, right? So that this is my Lie algebra. Now I take a initial condition. That's U0. That's this guy right here. And I issue a geodesic. I shoot a geodesic in this direction. So I take that initial vector. Here is the geodesic. This is my eta of t. And suppose I pick that point and I take the corresponding tangent. So now it's eta dot. I'll use this. So this is the tangent. And then I translate these tangents, all the tangents that I collect from that geodesic, and I'll get them in here as a curve. That curve is u of t. That's this guy. This is a reduction. Right? This is a cotangent bundle reduction. If I rewrite everything in a different language, reformulate it. The point is that what's happening here downstairs is what I called earlier the Lagrangian picture. This is the Lagrangian description of the flow. These are the Lagrangian coordinates. That's downstairs in the tangent space. In the group. And in the tangent space here, that's Eulerian. That's where the PDE sits. The PDE lives here. Okay, so so this was Arnold's observation, but he did not work with the Sobolev category. So his was C infinity category. He only did this kind of formally, and in particular, one does not know whether given U0. If I write down U0 as an initial condition, say smooth divergence-free vector field, whether I can actually obtain a smooth solution of the Euler equations here. I mean, the smooth solution, smooth the curve as a geodesic, as a solution of the geodesic equations. When I work with C infinity categories as a Fréchet category, I have problems with even uniqueness. Well, there is no inverse function theorem, or at least not without certain conditions, like, say, in Hamilton's paper or Moser's approach. So in Sobolev category, this can be done, and this is precisely what Eben and Marsden set out to do. So here is Eben and Marsden's result, which I will formulate slightly differently. So the answer, by the way, to the following question, suppose that U0 is HS, HS divergence-free initial condition. Do I get the corresponding eta of T an HS geodesic, or HS solution of the geodesic equations, which I obtained from this variational principle of Arnold? The answer is yes. And in fact, Eben and Marsden proved in their big paper a lot other things, but analytically, or at least reformulated in this geometric language, their result can be formulated as follows. So the if S is greater than n over 2 plus 1, then the L2, the right invariant L2 metric, the one defined by Arnold, the kinetic energy metric, admits a well-defined exponential map, a Riemannian exponential map. Let me call it exp, add the identity, so it's exp sub E, from some open subset, defined on some open subset of the tangent space at the identity with values in the volumorphisms, which is a local diffeomorphism, which is, in fact, just as in finite dimensions, a local diffeomorphism. Okay. So, incidentally, let me say here what's this exp E. So recall, as in finite dimensions, as in finite dimensional Riemannian geometry, I can say define this exponential map to be simply eta of t, where this is the unique geodesic, the unique solution of these geodesic equations, the unique, let me call this L2, the unique L2 geodesic with initial conditions that it starts at the identity and has u0 as its initial velocity. So this is just as in finite dimensions. And in fact, that it is a local diffeomorphism, that this exponential map is a local diffeomorphism also follows from the same argument as in finite dimensions, because if this is well defined and smooth, I can compute its derivative just as in finite dimensions and show that at 0 it's just the identity between tangent spaces, and use Banach version of the inverse function theorem for this statement. Okay, but how to find this? Well, this is the main point of the main analytic result of Eben and Marsden, and perhaps one way to explain this is the following. Let me just say main point. Proof of Eben and Marsden, main analytic point. So the main analytic point is the following. The L2 geodesic equation. This is what they found. The Euler equation, as suggested by Arnold, when rewritten after this change of the dependent variable as the geodesic equation on the diffeomorphism group, is in fact an ordinary differential equation. This was surprising, certainly surprising at the time. I think it still should be surprising a little bit, because it almost never happens. I mean, one doesn't expect when I write, say, equation like something like this. There is no way I can make this into an ODE. This is densely defined. It's I develop some nice complicated theory, and I can deal with this somehow, and I can get very nice results. But this is not an ODE. Now, this equation, system, turns out to be an ODE. Here's how. That's the main point. So let me start with the change of variables, which is kind of crucial here. I'm going to rewrite it in a slightly different way. So remember, t goes into eta of t is the curve in the volumorphism group. U is the corresponding solution of Euler, right? So this is the corresponding right translation to the tangent space at the identity of the tangent vectors to the curve. And dot means time derivative with respect to the parameter of the curve. So if I take the second derivative here, I'm taking here the time derivative, so I apply chain rule. and I get, well, let me write this, let me switch to dt. So I get so t is here and here. So I first take the t derivative of u. This is composed with eta. I take the eta outside. Plus, now I have to differentiate u, compose it with eta, and then take the derivative of eta, and apply this derivative of u to the eta dot. But eta dot is u composed with eta again. So what I get here is the derivative of u, but applied to u, composed with eta, applied to u composed with eta. So it's the derivative of u. It's on the manifold. It's the covariant derivative of the vector field u in the direction of u, and everything is composed with eta. Now, if I have that, then going back to where I was, right here, this is simply the minus of the gradient of the pressure composed with eta. So how do I get rid of that? Eta dot dot is equal to this. But now you see we have the divergence-free condition. So if I take the divergence of the first equation, what I get is this term drops out because u is divergence-free. This is minus Laplacian, depending on the sign, doesn't matter, minus Laplacian of p. And this is equal to the divergence of this nabla. So I can, from here, obtain the following. I can solve an elliptic problem on my manifold, compact manifold, without boundary, even with boundary. And I can write the gradient of p as minus gradient of the Laplacian inverse of the divergence of the covariant derivative of uu. So, so this goes in here, and it goes in here as, so the minuses cancel, and I get gradient, Laplacian inverse, divergence, covariant derivative. U itself is eta dot composed with eta inverse, and this is again eta dot composed with eta inverse. This whole thing is composed with eta. This is my right-hand side, f of eta and eta dot. Now, this is a vector field. One can show that this is in fact, smooth vector field on the volumorphism group of Sobolev class HS. How do we see this? Well, I mean, just looking at that, it's, well, maybe looking here, it's not difficult to see that it depends on eta and eta dot. It's not difficult to see that the dependence on eta dot is nice and smooth. Eta dot, basically, it's quadratic. This expression is quadratic in eta dot. That's fine. That's good enough. In eta, it's horrible. I have compositions here, there, inverses. It's not easy to see that. And I will not go there. But let me just convince you that at least this right-hand side maps into the correct space. If I take eta and eta dot to be HS, that I get something that is HS. Even that is not clear when you just look at this expression, because if, say, u is HS here, then I take the covariant derivative here. So this is HS minus 1. I take the divergence. That's HS minus 2. I take Laplacian inverse. That puts me back in HS. But then there's a gradient. So I land a little lower in HS minus 1. But it's not so bad because not everything is lost, because divergence-free constraint saves the day. You see, the divergence of the, so this is one of those nice Riemannian geometry formulas. The divergence of the covariant derivative of uu, if u is divergence-free, turns out to be basically, so if I take the trace with respect to the metric g of well, the square, really, of the gradient of u. We'll think of this as a matrix of first derivatives. So this is the first term. Then I have something which is lower order, Ricci of uu. So I'm saving one derivative here. And therefore, I land back in the HS space. OK, so this is how one actually can, well, then prove a little bit more and show that this is, in fact, a smooth map. Well, so OK, so Volibner's result. So what does Volibner's result mean in this geometric language? So if you recall, Volibner's 2D global Posedness in 2D, well, in this geometric language simply means geodesic completeness of the volumorphism group with the L2 metric. The 3D problem, therefore, would be establishing geodesic completeness in the. Oh, so let me be more careful here. M2. This is just the two-dimensional case, right? So that's the 2 here with the L2. And what is the exponential map? The exponential map can be viewed as the solution map of the corresponding Cauchy problem here in Lagrangian coordinates. So this is why I'm interested in the singularities of this exponential map and trying to understand using Riemannian geometric intuitions that we have, that we can develop here. So as you see, we can actually develop a lot of infinite dimensional, rigorously, a lot of infinite dimensional Riemannian geometry in this context of hydrodynamics. In fact, I think one point of view would be of Arnold was that hydrodynamics is, in this setting, is just a certain type of infinite dimensional geometry, like which is connected with the L2 metric and the group of volumorphisms, while symplectic geometry is another type of geometry, which is connected with another subgroup of the full diffeomorphism group, the symplectomorphism group. Okay, so what are conjugate points? So what are singularities? Singularities of the exponential map. So singular values. So this is our exponential map here, defined in this way. Then singular values of the Riemannian exp are the conjugate points in geometry. Conjugate points along geodesics. So recall from finite dimensions, kind of simplest example would be if we take S2, say in R3 with the induced metric from R3, and we take the north pole and the south pole, and geodesics on the sphere are simply great circles. So these 2 points will be conjugate. In particular, the way to interpret this is as say looking at the kernel of the derivative of the exponential map. It will have a one-dimensional kernel. In this case, if we have an Sn sphere in Rn plus 1 with the induced metric, then the corresponding kernel of dx at n here will be n minus 1 dimensional. So there is another description, more geometric perhaps, of conjugate points, is to look in finite dimensions, is to look at the solutions of the linearized geodesic equation, linearized along a geodesic, the so-called Jacobi fields, and look for zeros of these Jacobi fields. We start with a Jacobi field which is 0 at the initial point, and then if there is another 0, if the Jacobi field vanishes somewhere further on, then we'll have a conjugate point to the initial one. Okay, so what happens in infinite dimensions? So in infinite dimensions, we have a lot of pathological behavior. So for example, conjugate points in infinite dimensions are of 2 types. So there are 2 types. So in infinite dimensions, there are 2 types of conjugate points. Now this depends on, like in functional analysis, if we have a map, a linear map between, how can a linear map between 2 Banach spaces fail to be an isomorphism? Well, either acquires the non-trivial kernel or it's not onto. So these 2 types of conjugate points, these 2 mechanisms, of course, are just one mechanism in finite dimensions, but in infinite dimensions, we have to distinguish them. So we have to introduce 2 types, monoconjugate points and epiconjugate points. And this is, this is one complication. Another complication is that conjugacies may be of infinite order. So infinite order conjugacies of such points. For example, if we take a sphere S infinity, that's the simplest case. So e.g., if I take a sphere in the space of square summable sequences with induced metric, and I'll look at geodesics here. So this in L2 with induced metric. Then I'll have an infinite order conjugacy, and also conjugate points can accumulate along along finite segments, finite geodesic segments in infinite dimensions. So there is something known as Grossman's ellipsoid. So some of these things were studied also by people in functional kind of intersection of functional analysis and infinite dimensional geometry. And Grossman constructed a very nice ellipsoid. Again, this is an ellipsoid in L2, space L2 with the property that if we take intersections of this ellipsoid with R3, consecutive R3, so two axes will be fixed. This is x1, this is x2, and here we take, say, unit circle, and then on all the xk axes we'll have an ellipse, and this is, say, 1 over ak, so the equation here is this. And I want the AKs, so A3, for example, to be greater than 0, but less than AK, which is approaching 1 from below. So in other words, as I take consecutive Ks, I want to squeeze my football and make it look more and more like a ball. So if I take now this to be N, this to be S, this will be a geodesic. One can easily check this. Then my conjugate points will fall here and will cluster at S. OK. The question is, can these type of things happen in hydrodynamics? Well, the answer is no. The answer is it depends. More precisely, so this is the theorem, which I proved together with David Eben and Steve Preston. And I can formulate it as follows. So suppose Mn is compact Riemannian, no boundary. A boundary gives me problems. So then there are two statements here. The first statement is the following. Suppose that n is the dimension of n is 2. Then this exponential map at the identity, the L2x, is in fact a nonlinear Fredholm operator in the sense of, say, Smale. So Smale used these operators to generalize Sard theorem. So it's a nonlinear Fredholm operator in the sense that its derivative as a map dx e, say at tu0, as a map the tangent space to tu0 to the tangent space at identity at tu0, so I can identify it with just the tangent space at e to diff s mu into the tangent space at the point xe of tu0, oops, diff s mu. This map is a Fredholm operator. So it's bounded, in fact. So it's bounded, it's linear, it's bounded, it has finite dimensional kernel, finite dimensional co-kernel, and index 0. If n is equal to 3, or actually greater than or equal to 3, then no such luck. In general, no Fredholmness. OK, so this distinguishes two-dimensional and three-dimensional hydrodynamics. What this says is that none of these pathologies happen. There is just one type of conjugate points by dimension count. Index 0 means my epi and my mono have the same finite dimension. No infinite kernels. So no infinite conjugacies, no accumulations. In 3 dimensions, we can have accumulations. What does it mean? That's an interesting question. I don't know yet. Hopefully, it will be saying something about 3-dimensional hydrodynamics. Let me point one more result, which is a little bit more recent. It's this time is with Steve Preston. So if we take the diffeomorphism, the volumorphism group, I have to take sufficiently high S. and I take this, okay, so again, compact Riemannian, n-dimensional compact Riemannian manifold without boundary. And rather than take L2 metric on right invariant metric on this space, I take an HR metric. So this is why I need this S to be sufficiently big. So this is my right invariant. So I take the HR inner product at the tangent space at the identity, and then I do the same trick as before. I right translate it. So I get a right invariant metric, HR Sobolev metric. Then it turns out that I'll just state the relevant thing, that if in 3D, if R is greater than 0, then the HR exponential map, like here we had the L2x, there one can prove that there exists a well-defined exponential map for the HR case as well, is nonlinear Fredholm, also nonlinear Fredholm. Nonlinear Fredholm of index 0. Now, what this is saying is that the failure, from this point of view, the failure of the L2 Fredholmness in 3D is borderline in this sense. Again, I don't know yet. This is a result from 2010. I don't know yet what this means. My hope is, one hope is that perhaps because this is borderline, I can capture the failure by some spectral analysis. So what does it mean that I have an operator of index 0? And essentially, this is how one proves this Fredholmness result, here or here. There are now, by the way, 2 proofs, maybe 3, because Sasha also has a slightly different result on the quasi-ruled Fredholmness in hydrodynamics, which I still don't know yet what is precisely the relation. Maybe we can figure that out. But essentially, one of the proofs here proceeds by showing that quite explicitly that this dxT u0, well, let's forget t, just take t equal to 1, can be written as an invertible plus compact, so in 2 dimensions. So this is invertible operator, and this is, well, compact in 2D. I'm talking about L2x here. So for HRx, and I didn't write here, this is a 3D. This is a 3D result. I mean, in 2D, there is an even better condition. R has to be greater than -1/2. But it's a 3D that concerns me here. So if I take the, so just the L2, so then K is compact in 2D, but not compact. This operator is not compact in 3D. Now, if I take the HR, then it will be compact in 3D. So I can try to use, in principle, some kind of measure of non-compactness here. Look at essential spectrum of this, and hope to capture this failure. Maybe then use it to somehow identify certain directions at the tangent space at the identity, where I could, in which I could control the corresponding solution, 3-dimensional solution of the 3-dimensional Euler equation. Control by what means? By the means of having something like a lower bound on the injectivity radius. For example, for this I need good bounds on the curvature. So, okay, so the program here that kind of slowly begins to emerge is that one would like to use curvature estimates, injectivity radius estimates, as some kind of a priori estimates. So as playing the role of a priori estimates in the PDE approach. Of course, I don't know if this is doable. I can just hope that maybe it can, if nothing else, give some new insight into the problem, which is difficult. I guess it's I'm past my time, so thank you.
Thank you very much.